Hola, bienvenidos todos a 2084. Este episodio no va a ser como los demás, va a ser el primer episodio en inglés, así que presentaremos a nuestro primer invitado de habla inglesa. Hello, with us today we have a very special guest, Dr. Robert Beatty. Dr. Beatty, I was just telling the audience this is a very special episode in case you didn't know, not only because you are joining us, but you're also the first English-speaking guest of 2084. 2084 is a podcast where we have interdisciplinary conversations, interviews, and debates about technological disruption. We truly believe that having these conversations is very important if we want to make George Orwell fiction again. This is also the best way to battle against polarization and radical ideologies that are threatening democracies and weakening our ability to cooperate and respond to global problems like pandemics, climate change, and technological disruption. With this said, I give the word to my co-host Anton, who will introduce Dr. Beatty, and our good friend Pablo, who will co-host this episode with us.
Okay, so a little introduction into Dr. Beatty's career begins with his studies at the University of California, Berkeley. So go Bears, where he currently works as a senior lecturer. Dr. Beatty is a lecturer of immunology in the Department of Molecular and Cell Biology. He's also part of the Harris Research Program in the Division of Infectious Disease and Vaccinology. He's an expert in molecular biology, cell culture, and cell biology. And we're joined here today to talk about the polarization that exists surrounding the COVID vaccines. Also, before we start, I would like to thank Pablo, who was one of Dr. Beatty's students in his Plagues and Pandemics class, who will be accompanying us.
Hello, Santiago. Hello, Anton. I am very excited to join you guys in this episode. I also want to thank Dr. Beatty for taking time from his busy schedule to join us and help raise awareness of vaccine technology. And we're very excited about this talk and would like to start off by having Dr. Beatty talk a little bit on himself and how is it that he decided to work in this field?
So I used to work in the hospital and I used to work with patients all the time. And I became very interested in immune responses when my patients had diseases that are about the immune system attacking their own bodies. So because of autoimmunity, I became very interested in immunology. And then when I came to UC Berkeley to get my PhD, I actually joined a lab where we work on infectious diseases, and I worked on chlamydia. And I became very interested in infectious diseases as a PhD student. And then after I finished my PhD, I did a postdoc at Stanford and I worked on viruses, and I became more interested in viruses so that when I came back to Berkeley to teach, I ended up working only on viruses, though I have worked on parasites also. But I am basically an infectious disease immunologist where my specialty is working on infectious diseases.
Thank you very much for getting us to know you a little bit better. And first of all, I would like for the audience to understand the terminology behind the vaccines. So right now we were talking that all vaccines are active immunization. So if you would like to talk just like a very general understanding of what is an active immunization.
That's great. An active immunization is something that establishes memory. If you have immune memory, then that is an active immunization where the person who is given the vaccine or the person who's given the immunization will establish their own T cells, their own B cells, and their own memory, which we call immunity. So that we say you're immune to something if you have immune memory. So in that sense, an active immunization provides memory that should last for the rest of your life, or at least as long as that memory will survive. The idea behind an active immunization is that you are establishing your own memory rather than you're having immune protection from something else that's transferred.
That's very helpful to, I think, to understand this terminology. And building on that, I think it would be great if you could also just, it's pretty self-explanatory, I believe, but just it's important to mention the difference between the preventive and therapeutic vaccines.
Sure. So the idea behind a preventive vaccine is that it's given to you before you get the infection. And so you're preventing the disease from getting infection. I think very importantly, vaccines are about preventing disease, not about preventing infection. And I think a lot of people confuse that, which is that vaccines have always been made to prevent severe disease, not to prevent any symptoms, not to prevent infection. But even the SARS vaccines were tested for their ability to prevent hospitalization. They were not to prevent infection. They were not to prevent mild disease. They were to prevent severe disease. And so when you think of a preventive vaccine, it's about preventing a certain hallmark of severe disease. So many vaccines are about preventing very severe disease, but they don't often prevent infection. In fact, many vaccines don't even seek to prevent infection. And so I think it's very important to understand the difference there. A therapeutic vaccine is given to you when you have the infection. So a classic example of this is that if someone's exposed to rabies, they're given the therapeutic vaccine to prevent the disease of rabies, even though they already have the infection of rabies. And so a preventive vaccine is always used if you have never been infected with that exact pathogen or that exact strain of the pathogen. So that's very important to understand. We get a new influenza vaccine because it's a new strain of influenza. So it's still considered a preventive vaccine. You don't get the vaccine, even if you've already been infected with influenza, it's a new influenza. So there it's preventing the new influenza from causing severe disease.
It's great that you're clarifying that point. Right now, in a few questions, we're going to clarify more about the efficacy of the vaccine. But there are many people right now scared about the COVID, what you just said. They think it's to prevent infection, but it's not. So that's a very important point related to the COVID scare that exists in the world right now.
Absolutely. And it's really, none of the vaccines that we make usually are going to prevent infection. Most of them prevent severe disease. That's just the way it is. And I think it's very important to differentiate those things. The good thing about that is that if you are given the vaccine and you still get infected with SARS, you now have immunity from the vaccine and you have your own natural immunity from getting the infection. So getting the infection is a booster, which is helpful for you to have better memory. The vaccine is just supposed to prevent you from having severe disease. But if you still get infected again, that's really helpful to make your own immunity. So I think it's important. I got 3 doses of the vaccine and then I still got infected. And my friends who are immunologists say, well, your infection is now your 4th booster. You're just even more protected. And that is the way to think of it, I think, as.
That's really interesting. Dr. Beatty, Pablo shared with us some slides about your class to help us prepare for this conversation. And now I wanted to ask you something regarding attenuated versus inactivated vaccines, which are ones that have live viruses versus dead viruses. So I wanted to see if you could explain to us a little bit more about that.
Well, if the virus can infect a cell, if what you're given is live and it can actually replicate, we call that a live vaccine. And a lot of vaccines are attenuated forms of the pathogen so that they can still infect and replicate, but they cannot cause disease. So when vaccines were first made, this is how many vaccines were made. The original smallpox vaccine, the original polio vaccine were attenuated forms of the pathogen. They were weakened so that they could never cause disease, but they could still stimulate an immune response. Now we have live vaccines that are like the adenovirus vaccines that are subunit vaccines, but they're alive. And so live vaccines have an advantage where you can use less and they actually are better at targeting certain types of pathways and certain types of immune responses. But it is harder to make them and it's harder to use them again and again. So there's lots of pluses and minuses to the different types of vaccines. But in general, live vaccines versus inactivated vaccines is the kind of 2 general topics. And with the SARS virus, we definitely have some live vaccines that are adenovirus vaccines, and we have vaccines that we wouldn't call live vaccines that are the mRNA vaccines. They don't replicate, they don't make any copies of themselves. They just go in and make protein.
Now that you mentioned the SARS-CoV vaccines, I actually wanted to ask you, Professor, or Dr. Beatty, during class last semester, we saw a bunch of different types of vaccines. Like we just mentioned, the live attenuated and the dead virus. And we also talked about recombinant protein vaccines. Would you say those are part of which side?
Recombinant protein vaccines are what we call not live vaccines. Anything that can't replicate is an inactivated vaccine. So I think it's important that the main point of having it's either a live vaccine or it's not a live vaccine. So obviously a recombinant protein vaccine is not a killed vaccine. Yeah. It's just not a live vaccine that can replicate. It's just a piece of the pathogen that you're given.
What would be an example of a recombinant protein vaccine?
Recombinant protein vaccines are the hepatitis B virus vaccine and the human papillomavirus vaccine. Those are the two vaccines in humans that are recombinant protein vaccines. There are SARS vaccines being tested with recombinant protein vaccines. There's one in China, and there's another one in, I can't remember where it's made, but there's 2 or 3 of the protein recombinant vaccines for SARS. They're not commonly used in most of the Americas, but there are some recombinant protein vaccines. Do you want me to talk about the 2 types of vaccines for the SARS?
Yeah. Please do.
The 2 types of vaccines right now for the SARS are almost all mRNA vaccines, which is of course the Pfizer and the Moderna. These are brand new types of vaccines. There's never been a human vaccine for mRNA before the Pfizer and Moderna vaccines. And then there's the adenovirus, which are what we call recombinant subunit vaccines. This is where you take a live virus that normally would not cause disease in humans, an adenovirus, and you take this adenovirus and you insert a gene from the SARS protein. And so many of the different vaccines, the Johnson & Johnson, the Sputnik, the AstraZeneca, all 3 of those are adenovirus vaccines, which is a live virus that does not cause disease in humans. And it cannot be spread from human to human. So it's a virus that goes in, infects our cells, makes a bunch of protein, and then that.
¿Se les trabó a ustedes?
Yeah, I think we lost him for a second.
Bueno, ahorita editamos esta. Yeah.
So the vaccines that are adenovirus vaccines are live vaccines, and that would include the AstraZeneca, the Johnson & Johnson, and the Sputnik are the 3 main vaccines that use adenoviruses. So these adenoviruses actually are genetically spliced to put in the gene from the SARS-CoV-2 virus. They put in the spike protein, and then when that virus infects a cell, it causes the production of the spike protein, and then the immune response is made to that spike protein. And so the good thing about that is that by infecting cells, you're stimulating the right kind of immune response for a virus. The only downside about adenovirus vaccines is that if you boost with the same virus again and again, you'll build up an immune response to the adenovirus, and then it won't be as effective. So that's the downside of the adenovirus vaccines. However, I think there's a lot of advantages to having an adenovirus vaccine and an mRNA vaccine and maybe another type of vaccine, because each of them is complementary for the immune response that you get from each.
Okay, and building off of this, the difference between mRNA and adenovirus vaccines, which has shown to be the most effective against COVID?
That's a great question. Mostly the higher efficacy has been with the mRNA vaccines with 2 doses. So the most effective has been with 2 doses of the mRNA vaccines. I do think it's important to understand that each vaccine has a different viral protein sequence. So they're using a different gene from each one. So of course, the closer the virus is to the genetic sequence that's used in that vaccine, the more protective it will be. So clearly, some vaccines will work better if the virus that's being transmitted is the same exact virus as the viral strain that was used in the vaccine. So you have to keep in mind that all of them are effective, but some of them are more effective if they're closer to the actual vaccine virus that's spreading at the time that you give the vaccine.
Professor, I hear a lot that you mentioned effective, and just to be clear, when you say effective, what do you mean by that? What does it mean to be effective?
Efficacy is defined as the number of people that will be protected from your disease. It doesn't mean preventing infection. It means preventing severe disease. And so the idea there is that if something's 90% efficacious, it means 90% of the people will not have severe disease.
Okay, that makes a lot of sense. It clarifies a lot of stuff, a lot of misconceptions.
It's very important. Yeah, it's very important to define that it's about preventing disease, severe disease, rather than infection.
And continuing with this idea of preventing diseases, imagine a dystopian scenario where there are no vaccines. What percentage of the population theoretically would need to be infected in order to develop the herd immunity?
I don't know if we really have that completely defined for SARS. It's different for each pathogen. Some pathogens you need to have over 90% protection to get herd immunity. So anything that's very infectious, you need a very high percent herd immunity. I would guess with the SARS Omicron variation or variant, you probably need over 90% herd immunity to get protection. But I don't think it's been defined. Some pathogens like influenza, if you have 70 or 80% protection, you probably can get enough herd immunity to prevent spread. I think it's important to understand that herd immunity is hard to define because if you look at the number of people who've been infected with SARS, they can get reinfected just like they can with influenza, just like they can with cold viruses. So there's many viruses that can infect us many, many times. So you're only protected against the variant that you were vaccinated or infected with most recently. So the herd immunity is the people who are protected from having the infection and spreading it to other people.
Okay.
Doctor, right now that you mentioned influenza and the flu, what is the difference between these vaccines and the COVID ones?
The influenza vaccines are inactivated vaccines. They're actually grown-up viruses, and then they're inactivated, and then they're injected into your arm. This is a very expensive process for making vaccines, but it's the one that people use mostly for influenza because they believe that it's the fastest way to make a new vaccine every year. We don't have any inactivated vaccines that's very commonly used for SARS. The only inactivated vaccine was developed in China, and it's not very commonly used outside of China. The other vaccines, there's lots of other inactivated vaccines that were given, but the main one we're given every year is the influenza vaccine. That's the main inactivated, but it's a very different type of vaccine. It's grown in eggs, and then they collect the virus from the eggs, and then they kill the virus, and then they inject the virus.
And Professor, why don't they try to develop a new mRNA vaccine for influenza?
Oh, I'm sure they are trying to develop it right now.
And
I guarantee you they're trying to develop one right now.
Okay.
And speaking about mRNA, there was a lot of speculation in the beginning, and well, still a lot of people are continuing that they're scared about changing their DNA. So could you go a little bit more in depth into what an mRNA vaccine actually is, even though you already specified, but how is it that it doesn't change your DNA?
No, the mRNA vaccine is RNA that will get inside your cells, but mRNA cannot change DNA. So there's no DNA that can be changed by your RNA. So mRNA that comes from the outside would go into the cells to make protein, but mRNA cannot affect DNA. There's nothing it can do to all DNA. And this mRNA that you're given as a vaccine is put into vesicles of lipids so that it will specifically get taken up into the cell so that it can make protein. This is not something that can go to the nucleus. It can't go to where the DNA is in the cell. These lipids are literally treated or created so that they will provide the maximum ability for the mRNA to get into the cell so that it can make protein. And so I think that's the important thing to understand, is that this mRNA is targeted once it gets to a cell so that it will make protein. There's no other place for the mRNA to go to.
That's very interesting, Professor. And I would also love for you to respond why is it that the vaccine was developed so quickly, or many people are skeptical about this part, like
Yes.
why should we trust vaccines? Well, this vaccine was made in a record amount of time, it was like,
but you have to understand that they were already using the technology to make a MERS vaccine, and MERS is another another coronavirus. So there's SARS-1 and MERS and SARS-2, and the SARS-2 happened to come out after we were trying to make vaccines for MERS. And so the same technology that was being used to make the MERS vaccine was already in place. And so it wasn't very difficult to take what they already had developed for MERS, and they were using the same spike protein on MERS, and then put in the same gene from SARS, or the different gene from SARS. So because the technology was already under place, and because they'd already tested many of the things with the MERS virus, it wasn't very difficult to change to a new coronavirus. So you have to imagine that when SARS-1 happened, there was a lot of new technology for coronaviruses. And then when MERS came out in like 2012, there was a lot more technology for coronaviruses. And so when this came out in 2019, 2020, there's all the technology that's been around for 17 years and 10 years that was already available, that was useful with coronaviruses. So all of this technology has been built up over the last 18 years. So the approval process was fast and the testing was done very quickly, but the technology has been around for a long time, and the mRNA technology has been gradually developed over the last 15, 20 years. I mean, go ahead.
No, I also understand that there was like a surplus, or not surplus, but that there was a lot of volunteers also, or there was no, that they usually, that's a problem in.
That is very true. And they did very quick animal testing. And one good thing about SARS is that if you get exposed to it, you either get sick or not within a week. So those kinds of things made a big difference, right? And because the infection rate was higher, they could test it in areas with a lot of SARS, so they could get results much quicker for a clinical trial. So not only were there lots of volunteers, but because SARS was spreading quickly and in many areas, it was a lot easier to find places to test, right? So you can test it in many, many areas because there's lots of virus spreading. And that's not always so true. So a lot of pathogens, a lot of virus vaccines take a long time to test, because if the pathogen is not spreading quickly, then it doesn't get tested as quickly.
And I have another question, actually. Do you think you could walk us through what is the process in a vaccine? Like
How to make the vaccine?
Yeah.
How to make the vaccine or how to test the vaccine?
Either works, I guess.
So how to make the vaccine is you have to identify the key pieces of the virus that will make the best immune response. So with SARS, the key antigen or the key protein that is used for the immune response is the spike protein. And so that is the protein that's used in most of the vaccines. So they already knew this. Again, they already knew this because of MERS and SARS-1. So we knew this before SARS-2 happened. It was confirmed very quickly that it was the best protein antigen to use for the vaccine. So that was not very complicated because we already knew this from other coronaviruses. Once you have the identified antigen or the identified protein you're going to use in your vaccine, you then need to figure out how to put it so that you'll get the maximum activation of the immune response. This is first done with cells, and you do this in cells where you test cells and you look at different ways to give the protein, give the vaccine part. So you can do that with adenovirus. You can test it with inactivated viruses. You could test that with this mRNA vaccines. There's DNA vaccines. There's mRNA vaccines. There's protein vaccines. So you do all of that in cells. Then, if you get a good immune response and you can stimulate this in cells, you then would test it in animals. And then in animals, you do this with injections, and then you test whether or not you can protect against infection with severe disease. So you're trying to prevent severe disease again. And then after animal testing, there's
Excuse me,
stages.
Dr. Beatty, sorry for interrupting.
No, it's fine.
Which animals do you use? Are there any specific kind that relate to humans, or they don't have to, or their DNA doesn't have to relate that much to humans?
Usually they tested it in rhesus monkeys after they tested in mice. So it's usually mice and then monkeys.
Okay. I'm sorry for interrupting. Please
that's
continue.
fine. Mice and the monkeys. I didn't want to get into too much animal stuff. Then after that, there's 3 stages to testing in humans. The first stage is testing safety. And then the second stage is testing for efficacy in a small number of patients. And then the final stage is testing for efficacy in a large number of patients. So those 3 stages were all done somewhat at the same time. After the safety was determined, they could test in small numbers and large numbers. So that is one of the reasons it was so rapidly approved, is because they could test those things more quickly. As Pablo said, there's more volunteers that were available, and they could test on a larger scale because there was more infection around. So if you vaccinate 200 people and you don't vaccinate 200 people, you see how much infection happened in the 200 people that didn't get vaccinated. And then you see how much severe disease infection happened in the people that did get vaccinated. It happens more quickly if more people getting infected in a population. So the reason that these mRNA vaccines, the adenovirus vaccines, got approved so quickly is because they were tested in areas where there were lots of infections. So only because there were so many infections was it able to get efficacy data quickly.
Dr. Beatty, and what do you believe is going to be the future of vaccines with all of the new technology that is available?
The future of vaccines for SARS, or the future of all vaccines?
For mRNA and DNA vaccines.
I think mRNA vaccines it's amazing. I didn't believe mRNA vaccines would be this successful. It has been very surprising. I am surprised and impressed that vaccines have been so successful. It's really, the mRNA vaccines have been so successful. I think that adenovirus vaccines have been around, and they are showing that they are more versatile with SARS than they have been with some other pathogens. I think that in the future, there'll be other types of SARS vaccines. I think we'll continue to get we'll have some recombinant protein vaccines. I think we'll have other vaccines, maybe some inactivated vaccines. And I think all of those together will work to provide protection when you have new variants. So I guess my imagination is that there'll be new variants of SARS, and we'll have to have new vaccines to deal with the new variants. But it's very hard to predict because we just don't know how fast it's going to change. So it might be that you get a yearly vaccine like you do with influenza, or it might be that only when there's a new variant would you need a new vaccine, which might happen every 2 years, right?
Okay, it's really interesting to see how you picture that, even though it's impossible to know what the future is going to look like.
It's impossible to know. Yeah.
But I think we've covered a lot of technical parts, and I really wanted to ask you about a little bit of your personal opinion as a scientist. How do you feel personally with, for example, the vaccine mandates, vaccine passports, and all of these political topics that have caused a lot of controversy around the world?
Oh, well, I'm a big believer in vaccines. And I think vaccines have saved more lives on a dollar-by-dollar basis than any other thing that's happened in any immunology, any medicine, in any way or shape or form. vaccines have saved the most lives for the least amount of money. So I think it's impossible not to agree with that. And so, of course, I think vaccines are super important. I think it's very difficult to decide how to tell people and convince people when they disagree with that. But of course, I do research on vaccines. I believe in vaccines, and it's very hard for me to see otherwise. But I do think that it's very challenging when people challenge public health with something that's not about science, or with something that's not about kind of clinical medicine. And I do think there's a lot of misperceptions about what vaccines are supposed to do. And I think that's the really sad part, is that people think that because we don't have a lot of disease now, the vaccines don't do very much. But the truth is that if it weren't for vaccines, we'd still have people dying every year of measles, and people dying every year of mumps, and all these different pathogens that are protected by vaccines now. And people are unaware of what a difference vaccines make still to this day for everything that is still a problem, still a pathogens. So
have you ever encountered someone that is refusing to get the COVID vaccine shot?
Oh yes, people I know, people I'm friends with.
And what do you tell them? Do you explain the science behind them, or they don't care?
It depends on the person. It's very important to understand people's reasoning.
Okay.
I think for a lot of people, the fear of change and the fear of something unknown is really the greatest fear.
Okay.
I don't think that it really depends on whether or not it's a political or a personal or a actual professional or scientific reason that they have that. So it really depends on that.
Okay.
Sorry, is that
no? I understand you. I also have family members and a very good friend of mine who feel the same way. But finally, just to end this this great conversation, I have more of a personal question. Especially here in Berkeley, this technology was developed, the CRISPR-Cas9 technology, and I wanted to get your point of view on that.
On the CRISPR-Cas9?
Yeah, what do you think the applications will be in the future?
Oh, I think it'll be really amazing if we can actually get it to work in cells that will then go into people. But I think it's a far cry away from therapies that will work in people directly. I mean, as a technology for research, it's amazing, and it's done amazing things. But as a technology for clinical promise, I'm not sure it's as easy to do as people think it is. But
so
I mean, I don't know. I don't know enough about the stem cell therapy ideas, but it's a pretty interesting idea.
So a future like Gattaca is still far away from us.
I think so. I think that's quite a far away.
We hope so. We don't
Gattaca's, yeah, I don't think it's very close.
We don't want genetic profiling.
The biggest promise right now is if someone had paralysis from a broken spinal cord or a damaged spinal cord.
Okay.
If you could go in and fix that, that would be amazing, right?
Amazing.
Or if someone had a bone marrow cancer or leukemia, and you could go in and fix that, those are the most promising therapies through CRISPR that I think most people are working hard to make those work. There's no question that cancer therapies and injury therapies are the biggest promise with CRISPR. And of course, like, cystic fibrosis, I mean, those kinds of diseases, genetic disease where you could fix the defect, that would be, that's the holy grail for CRISPR diseases.
Without a doubt. Without a doubt.
Yeah.
Talking about CRISPR, and we also mentioned DNA vaccines. How do DNA vaccines work? Do they exist, or are they in the works, or?
They do exist. There's none approved for human use. There are some for animal use. There's none for human use. They haven't been as easy to make as we thought they would be. And I think that is a good question of why they haven't worked as well. I think that it hasn't been for lack of trying, but you don't need CRISPR to make a DNA vaccine. It's pretty easy to make a DNA vaccine. What's difficult is to deliver the DNA vaccine and make sure it goes into the right cells. The difference with the mRNA vaccine is it can go into lots of different cells and it still works. The DNA vaccine, if it goes into the wrong cells, doesn't work. So even though DNA vaccines do work in animal models, they haven't really proven to be as effective in human testing. So I guess I think DNA vaccines still hold promise. I just haven't, I don't know why they haven't worked so well, actually.
Well,
Yeah, go ahead.
Oh, I just wanted to thank you a lot for your time, Dr. Beatty. It's been a very interesting talk. I'll make sure to send this to the family members and my friend I was telling you about, and hope to get their knowledge up and hope they get vaccinated real soon. But
Yeah,
it was a very
I think
interesting talk.
it's very difficult. I definitely have people who were against vaccines. I would say, but interesting though, there's definitely a number that were against vaccines have ended up getting vaccinated in the end.
Okay, that's good. That's good.
Yeah.
Well, Dr. Beatty, I also wanted to thank you very much for your time. I think we all learned a lot. And well, thank you as well to Pablo for inviting you. We hope to have Pablo more often here on 2084.
Thank you.
Okay.
thank you very much, Professor.
You're welcome, of course. I'm happy to try to help.
It was great to apply some of last semester's knowledge
Good.
on this podcast. Yeah, I loved it.
Good.
Well, thank you very much. Take care, Dr. Beatty.
Okay. Thanks very much,
Thank
guys. Good luck with it all.
Thank you.
Appreciate it.
Dr. Beatty, before you go, do you have any social media we can contact you in order to
I do have
promote the
have
episode?
Instagram. I don't
Okay.
have, I have Facebook, but I never use it. But I do have Instagram.
And Twitter or LinkedIn?
I have LinkedIn. You can find me on LinkedIn.
Okay,
Yeah.
great. What's your Instagram handle?
That's a really good question.
Okay.
I'm not sure I want to tell this to the entire blog,
No,
but I'll tell you guys.
Okay.
Just for you guys, I don't really put much on Instagram, but I think it's PRBINSF. PRBINSF. So LinkedIn, I use more the professionally, and that's where I connect with students. Instagram is with friends.
Okay.
We can.
Okay.
I don't know. I don't think if Instagram is serious enough to do anything
Professional. Okay.
No, just send a link through LinkedIn, I believe, via LinkedIn.
Yeah, LinkedIn is probably the easiest.
But
I
don't,
think of Instagram as, at least in my world, Instagram is free from the politics of it all.
Yeah. No, if you don't want to for us to tag you in the pictures, we won't. We'll just.
Oh yeah.
Okay.
No, probably better not to in the
Okay.
Instagram.
Perfect. Well,
I mean, you know.
It's your choice. It's your choice.
Yeah.
Thank you very much, Dr. Beatty.
LinkedIn. Oh, you're welcome.
Great.
So Santiago, you're the
Thank
one
you.
that in Mexico?
Yes, I am here in Mexico City right now.
I see. You're holding down the fort until Pablo and Anton come back.
Yeah. Well, I'll hopefully visit them soon in Berkeley.
You should.
Yeah,
You
I
should.
guess-
It would be great.
Yeah. Well, if you come to Berkeley, you come visit me, Santiago.
For sure, Dr. Beatty.
sure.
It would be a pleasure. It was a pleasure to talk with you today.
All
Great.
right. Good luck, guys.
Good luck.
Thank
Thank you
you.
very much.
Thank you.
So sorry about the
No, don't worry. Don't worry. Everything worked out perfect.
craziness. Okay, take care.
All right. Thank you.
Bye.
Bye. Bye.